Hello. All right. So, what did we do last time? Last time we didn't implement that much. We read a little bit about hyperparameter tuning. We implemented this learning schedule thing, which isn't really about hyperparameter tuning, but it's about changing the learning rate as we go. Between streams, I happened to just try my ReLUs again, and they worked this time. So I don't know what we've changed that now makes ReLUs work. I didn't think we changed anything that would impact that, but ReLUs are now working. So I'm gonna switch to using ReLUs. I think I can I even use ReLUs in the output layer? Kind of, it kind of works, but softmax is the one that makes the most sense to me as an output layer. So I think we're gonna use, we start on 93.8, which is great. I think I'm gonna use ReLU and softmax, ReLU for the hidden, softmax for the output from now on. The other thing I'm gonna do is, ReLUs are pretty slow, and I found a way to do it that is faster. So instead of calling this max function and then vectorizing it, if I just do this, so z times, and this doesn't make sense when z is a array, although NumPy seems to get what I'm trying to say and vectorizes it correctly. So if you do z times z greater than 0 and 1 times z greater than 0, in Python, if this number is greater than 0, then this thing becomes true, and true works the same way as the number 1. So this is saying z times 1 if it's positive and 0 if it's negative, which is exactly what I want. And same here, 1 if it's positive, 0 if it's negative. Actually, I might be able to get rid of the 1 times on that one. There it is. So now that is working a lot faster. Does it make a difference with a 1 times right there? No, same thing. All right. So yeah, look at that. We get to 96 after like 9 iterations, even less. Is there any other kind of cleanup that I want to do before we get into the next part? No, I think that's about it. All right, so let's move on. Other techniques. Each technique developed in this chapter is valuable to know in its own right, but that's not the only reason I've explained them. The larger point is to familiarize yourself with some of the problems which can occur in neural networks and with a style of analysis which can help overcome those problems. In a sense, we've been learning how to think about neural nets. Over the remainder of this chapter, I briefly sketch a handful of other techniques. These sketches are less in-depth than the earlier discussions, but should convey some feeling for the diversity of techniques available for use in neural networks. Variations on stochastic gradient descent. Stochastic gradient descent by backpropagation has served us well in attacking the MNIST digit classification problem. However, there are many other approaches to optimizing the cost function, and sometimes those other approaches offer performance superior to mini-batch stochastic gradient descent. In this section, I sketch two such approaches, the Hessian and the momentum techniques. Hessian technique. To begin our discussion, it helps to put neural networks aside for a bit. Instead, we're just going to consider the abstract problem of minimizing a cost function c, which is a function of many variables, w equals w1, w2, etc. So c equals c of w. By Taylor's theorem, the cost function can be approximated near a point w by c of w plus delta w equals c of w plus sum of the gradients of the w's times the deltas of the w's plus the plus 1/2 times the sum of the second or the partial derivatives of c with respect to two different w's times delta wk plus, and then it goes on infinitely with higher order gradient, or yeah, higher order terms. We can rewrite this more compactly as c of w plus delta w equals c of w plus gradient of c dot product delta w plus 1/2 gradient of w transposed times h times delta w plus etc., where grad c is the usual gradient vector and h is a matrix known as the Hessian matrix, whose jkth entry is derivative of c with respect to wj and wk. Suppose we approximate c by discarding the higher order terms represented by ... above. So now we've just got approximately equal, and we don't have the terms after the first two. Using calculus, we can show that the expression on the right-hand side can be minimized by choosing, and then footnote. Strictly speaking, for this to be a minimum and not merely an extremum, we need to assume that the Hessian matrix is positive definite. Intuitively, this means that the function c looks like a valley locally, not a mountain or a saddle. Okay, take your word for that one. So delta w equals negative the inverse of the Hessian times the gradient vector. Provided 105 is a good approximate expression for the cost function, then we'd expect that provided this is a good approximate thing. Then we'd expect that moving from the point w to w plus delta w would be equal to w minus inverse Hessian times gradient vector should significantly decrease the cost function. This suggests a possible algorithm for minimizing the cost. And what we've been doing so far is just taking this. So this is saying, here's an even better approximation, I think. Choose a starting point w, update w to a new point w prime equals w minus inverse Hessian times grad c, where the Hessian h and grad c are computed at w. Update w prime to a new point w prime prime equals w prime minus Hessian prime inverse Hessian prime. Gradient prime c, where the Hessian h prime and grad prime c are computed at w prime. That's a weird way of saying just keep doing this in a loop. In practice, 105 is only an approximation, and it's better to take smaller steps. We do this by repeatedly changing w by an amount. Delta w equals negative eta inverse Hessian times grad c, where eta is known as the learning rate. This approach to minimizing the cost function is known as the Hessian technique, or Hessian optimization. There are theoretical and empirical results showing that Hessian methods converge on a minimum in fewer steps than standard gradient descent. In particular, by incorporating information about second-order changes in the cost function, it's possible for the Hessian approach to avoid many pathologies that can occur in gradient descent. Furthermore, there are versions of the backpropagation algorithm which can be used to compute the Hessian. If Hessian optimization is so great, why are we using it in our neural networks? Unfortunately, while it has many desirable properties, it has one very undesirable property. It's very difficult to apply in practice. Part of the problem is the sheer size of the Hessian matrix. Suppose you have a neural network with 10 to the 7 weights and biases. Then the corresponding Hessian matrix will contain 10 to the 7 times 10 to the 7 equals 10 to the 14 entries. That's a lot of entries, and that makes computing inverse Hessian times grad C extremely difficult in practice. However, that doesn't mean it's not useful to understand. In fact, there are many variations on gradient descent which are inspired by Hessian optimization, but which avoid the problem with overly large matrices. Let's take a look at one such technique, momentum-based gradient descent. Momentum-based gradient descent. Intuitively, the advantage of Hessian optimization is that it incorporates not just information about the gradient, but also information about how the gradient is changing. Momentum-based gradient descent is based on a similar intuition, but avoids large matrices of second derivatives. To understand the momentum technique, think back to our original picture of gradient descent in which we considered a ball rolling down into a valley. At the time, we observed that gradient descent is, despite its name, only loosely similar to a ball falling to the bottom of a valley. The momentum technique modifies gradient descent in two ways that make it more similar to the physical picture. First, it introduces the notion of velocity for the parameters we're trying to optimize. The gradient acts to change the velocity, not directly the position, in much the same way as physical forces change the velocity and only indirectly affect position. Second, the momentum method introduces a kind of friction term which tends to gradually reduce the velocity. Let's give a more precise mathematical description. We introduce velocity variables v equals v1, v2, etc., one for each corresponding wj variable. Footnote: in the neural net, the wj variables would of course include all weights and biases. Okay. Then we replace the gradient descent update rule, w goes to w prime equals w minus eta grad c, by v goes to v prime equals mu, or nu? How do you pronounce this? Is this mu? Mu. Mu v minus eta grad c. So v is changing the same way that w was changing, except we've got this term here, the mu times this minus that, which looks kind of similar to what we have as our regularization. Where is regularization? Right, so we've got we multiply weights by some number that makes it a bit smaller, and then we subtract eta grad c from it. Okay, so they're saying don't directly change w by this. Instead, keep track of a v that's like a velocity, change the velocity, and then use the new velocity to update w. In these equations, mu is a hyperparameter which controls the amount of damping or friction to the system. To understand the meaning of the equations, it's helpful to first consider the case where mu equals 1, which corresponds to no friction. When that's the case, inspection of the equations show that the force, grad c, is now modifying the velocity v, and the velocity is controlling the rate of change of w. Intuitively, we build up the velocity by repeatedly adding gradient terms to it. And I'm looking here to, if mu is 0, that means there's infinite friction, which means this is always 0, and you're just back to how we were doing it before. Okay, well, I can do this. Mu float. right? And this is the coefficient of friction. And this is the learning rate. So that would mean right over here. How do I say this? I guess I don't know when the velocity resets. Does it reset after the end of the mini batch, or does it persist forever? Let's say it persists forever. So mu equals mu. Let's pass mu down from here. I don't know what to set it at. Something between 0 and 1, I know. Okay, so mu. I want to remember it as I'm training. So why don't we start by setting self dot velocity, velocities, because you've got one for each. I guess you've got W velocities and you've got B velocities. Maybe I'll set them up here. What do they start as? Maybe they can start as 0. So looks like this for biases. And for weights, it'll be like this, except zeros. Because this should be basically np dot zeros xy. Do you have to put that in like that? Okay. So there's my W and B velocities. Then when you start training, well, whatever, we don't need to worry about what happens if you train more than once. But here, self dot W velocities equals, so first you multiply the friction, which is mu, yeah, it's just times equals mu for both of them. At I. And then you do this thing. W velocities, B velocities, and then here W velocities of I. Okay, I think I've implemented momentum. How does it work? I think I must have one of my initializing things backwards here. Is this y comma x? All right, we're barely learning. What's the issue here? It's hard to tell what the issue is when these things happen because the issue shows up somewhere else. It's showing up like in the softmax, which just means that we did something wrong somewhere, but it's hard to tell what. I don't know what we've done wrong yet. This thing is kind of in the way. I'm just gonna comment it out because I'm not using it, just so I can skip over it more easily. So V, you multiply it by the coefficient, then you subtract. I guess I'm assuming that it's the over M thing like before. Maybe it's a hyperparameter issue also, because I guess I would be moving way faster than before, so maybe I need a way smaller learning rate. What if I make it way smaller? 100 times smaller. Nope. Okay, so if this is 0, that should work the same as before. So if this isn't working the same as before, I've implemented it wrong. Okay, I've implemented it wrong. So what's the issue? No way to know because the issue is an overflow later. Oh, wait. These should be plus equals now. Oh, yes. Okay. So that should be working as before. And then what if I have actual friction? 0.5. It's working. It's not better. What if I have less friction? 0.1. Jumping around. Maybe what I need is, oh, that's not what I meant to change. Instead of having a constant schedule, try doing a, what did I call this? A decay schedule. Because I still have a feeling that learning rate should be smaller when you have momentum because you're gonna end up moving by more. I guess that's also what the friction is controlling though. This seems to be working, but... Oh yeah, I mean, this seems to actually be working really well. Yeah, that was crazy, 97. Maybe I just need to start with a lower learning rate to begin with. The cool thing about learning rate is that it can change to get to the right size as we go. So I don't have to tune it like the other parameters. I think this is actually working better than before. So that's pretty cool. All right, let's keep reading and see if we did it right. In these equations, mu is a hyperparameter which controls the amount of damping or friction in the system. To understand the meaning of the equations, it's helpful to first consider the case where mu equals 1, which corresponds to no friction. When that's the case, inspection of the equation shows that the force, grad c, is now modifying the velocity v, and the velocity is controlling the rate of change w. Intuitively, we build up the velocity by repeatedly added gradient terms to it. That means if the gradient is in roughly the same direction through several rounds of learning, we can build up quite a bit of steam moving in that direction. Think, for example, of what happens when we're moving straight down a slope. With each step, the velocity gets larger down the slope, so we move more and more quickly to the bottom of the valley. This can enable the momentum technique to work much faster than standard gradient descent. Of course, a problem is that once we reach the bottom of the valley, we will overshoot. Or if the gradient should change rapidly, then we could find ourselves moving in the wrong direction. That's the reason for the mu hyperparameter in 107. I said earlier that mu controls the amount of friction in the system. To be a little more precise, you should think of 1 minus mu as the amount of friction in the system. Yeah, mu is the amount of slipperiness. When mu equals 1, as we've seen, there is no friction, and the velocity is completely driven by the gradient grad c. By contrast, when mu equals 0, there's a lot of friction that the velocity can't build up, and the equation's reduced to the usual equation for the gradient descent. In practice, using a value of mu intermediate between 0 and 1 can give us much of the benefit of being able to build up speed, but without causing overshooting. We can choose such a value mu using the held out validation data in much the same way as we select eta and lambda. I've avoided naming the hyperparameter mu up to now. The reason is that the standard name for mu is badly chosen. It's called the momentum coefficient. This is potentially confusing since mu is not at all the same as the notion of momentum from physics. Rather, it is much more closely related to friction. However, the term momentum coefficient is widely used, so we will continue to use it. Okay, why don't I change my comment to say momentum coefficient. Where did I write that? Momentum coefficient makes more sense because it's the opposite of friction. It's not friction. A nice thing about the momentum technique is that it takes almost no work to modify the implementation of gradient descent to incorporate momentum. We can still use backpropagation to compute the gradients just as before and use ideas such as sampling stochastically chosen mini batches. In this way, we can get some of the advantages of the Hessian technique using information about how the gradient is changing, but it's done without the disadvantages and with only minor modifications to our code. In practice, the momentum technique is commonly used and often speeds up learning. Exercise. What could go wrong if we used mu greater than 1 in the momentum technique? You would exceed the speed of light. You'd build up more and more and more speed even when there's no gradient. Because you'd just be continuing to grow your velocity. What would go wrong if mu was less than 0 in the momentum technique? I think it would be the same in the other direction. It would be like you'd be biased against moving in the direction that you used to be moving, which like the whole point of using momentum is that in practice, moving in the direction you used to be moving is a good heuristic. So you would be doing the opposite of a good heuristic. Problem. And we did this, add momentum. Okay, other approaches to minimizing the cost function. Many other approaches to minimizing the cost function have been developed, and there isn't universal agreement on which is the best approach. As you go deeper into neural networks, it's worth digging into the other techniques. Understanding how they work, their strengths, and weaknesses, and how to apply them in practice. A paper I mentioned earlier introduces and compares several of these techniques, including conjugate gradient descent and the BFG's method, also known as the big fucking gradient stochastic method. See also the closely related limited memory BFGS method, known as LBFGS. Another technique which has recently shown promising results is Nestov's accelerated gradient technique, which improves on the momentum technique. However, for many problems, plain stochastic gradient descent works well, especially if momentum is used, and so we'll stick to stochastic gradient descent through the remainder of this book. I'm guessing that none of these other techniques are going to be very easy to implement, right? So this seems to be what we just learned. Is this the modified one? I guess I don't know what this F is. Was the F in the previous one? Oh, it was. F of theta. Oh, given a function to be minimized. Okay, so what's our equivalent of that? Well, we had, I think this is learning rate, eta. And then I guess F of theta is grad of W. But then here they're saying do F of something else. And I don't know how to do that. I'd have to modify my gradient descent to get a different, to get something other than grad W. So yeah, I don't know how to do that. And it doesn't explain it, does it? I don't know. I don't want to read this whole paper right now, because I probably wouldn't understand it anyway. Okay. Other models of artificial neuron. Up to now, we've built our neural networks using sigmoid neurons. Not me. I'm using ReLUs. In principle, a network built from sigmoid neurons can compute any function. In practice, however, networks built using other models of neurons sometimes outperform sigmoid networks. Depending on the application, networks based on such alternate models may learn faster, generalize better to test data, or perhaps do both. Let me mention a couple of alternate model neurons and give you the flavor of some variations in common use. Perhaps the simplest variation is the tan-H, pronounced tanch neuron, which replaces the sigmoid function by the hyperbolic tangent function. The output of a tan-H neuron, or a tanch neuron, with input x and weighted vector w and bias b, is given by tan-H of w dot x plus b, where tan-H is of course the hyperbolic tangent function. It turns out that this is very closely related to the sigmoid neuron. To see this, recall that the tan-H function is defined by this? Yeah, recall this, because I definitely knew that, and now you're just telling me to remember it. With a little algebra, it can easily be verified that sigmoid is equal to 1 plus tan-H of z over 2 over 2. That is, tan-H is just a rescaled version of the sigmoid function. We can also see graphically that the tanch function has the same shape as the sigmoid function. One difference between tanh neurons and sigmoid neurons is that the output from tanh neurons ranges from -1 to 1, not 0 to 1. This means that if you're going to build a network based on tanh neurons, you may need to normalize your outputs, and depending on the details of the application, possibly your inputs, a little differently than in sigmoid networks. Similar to sigmoid neurons, a network of tanh neurons can, in principle, compute any function, mapping inputs to the range -1 to 1. Furthermore, ideas such as backpropagation and stochastic gradient descent are as easily applied to a network of tanh neurons as to a network of sigmoid neurons. Footnote: there are some technical caveats to this statement for both tanh and sigmoid neurons, as well as for the rectified linear neurons discussed below. However, informally, it's usually fine to think of neural networks as being able to approximate any function to arbitrary accuracy. Exercise: prove the identity in equation 111. No, I'm not going to do that. I don't care to do that. That's not what I'm trying to get out of this book. Wait, but I need to know what tanh prime is in order to implement it. Derivative of tanh h. Sec h squared of x. All right, well, let's try it. ReLU. Here, let's copy the sigmoid one. Tanh h. Return np dot. I'm hoping that these just exist. Tanh h. Yep. Of z. And np dot seek h. Ooh, I don't have that. It's just secant though, right? NumPy secant. It doesn't have it. Okay, how about just NumPy derivative of tanh h? One minus the square of tanh h? Is that even true? Derivative of tanh h. I guess it is true. Okay. So here's our tanh. Let's import it here. And let's try using them instead of the hidden layer. It works. It works great. It's totally learning. All right. Which type of neuron should you use in your networks, the tanh or sigmoid? A priori, the answer is not obvious, to put it mildly. However, there are theoretical arguments and some empirical evidence to suggest that tanh sometimes performs better. Footnote. Oops. Footnote. See, for example, Efficient Backprop by Yann LeCun, and Understanding the Difficulty of Training Deep Feed-Forward Networks by other people. Let me briefly give you the flavor of some of the theoretical arguments for tanh neurons. Suppose we're using sigmoid neurons, so all activations in our network are positive. Let's consider the weights W, L plus 1, JK input to the jth neuron in the L plus 1th layer. The rules for backpropagation tell us that the associated gradient will be activation of LK times delta of L plus 1J. Because the activations are positive, the sign of this gradient will be the same as the sign of delta L plus 1J. What this means is that if the delta L plus 1J is positive, then all the weights W, L plus 1, JK will decrease during gradient descent, while if delta L plus 1J is negative, then all the weights W, L plus 1, JK will increase during gradient descent. In other words, all weights to the same neuron must either increase or decrease together. That's a problem since some of the weights may need to increase while others need to decrease. That can only happen if some of the input activations have different signs. That suggests replacing the sigmoid by an activation function such as tanh, which allows both positive and negative activations. Indeed, because tanh is symmetric about 0, tanh of negative z equals negative tanh of z, we might even expect that, roughly speaking, the activations in hidden layers would be equally balanced between positive and negative. That would help ensure that there is no systematic bias for the weight updates to be one way or the other. How seriously should we take this argument? While the argument is suggestive, it's a heuristic, not a rigorous proof that tanh neurons outperform sigmoid neurons. Perhaps there are other properties of the sigmoid neuron which compensate for this problem. Indeed, for many tasks, the tanh is found empirically to provide only a small or no improvement in performance over sigmoid neurons. Unfortunately, we don't yet have hard and fast rules to know which neuron types will learn fastest or give the best generalization performance for any particular application. Another variation of the sigmoid neuron is the almighty rectified linear neuron, or rectified linear unit. The output of a rectified linear unit with input x, weight vector w, and bias b is given by max of 0 and the weighted input. Graphically, it looks like this. If you're below the 0, you stay at 0. If you're above 0, it's linear. So I already implemented ReLUs because I know, or I've heard, that in practice, these are the best neurons. And we've also seen that like it works better than tanh for us. We got to 97 a second ago. Yeah, we're probably going to get to 97 on this also. Eta is going to go down eventually. Maybe we won't. Maybe not in the amount of time that we have. Okay, Eta went down and now we're at 97. Good. So yeah, ReLUs in practice have worked well, and I think like outside this book are the main neuron that people use. Obviously, such neurons are quite different from both sigmoid and tanh neurons. However, like sigmoid and tanh neurons, rectified linear units can be used to compute any function as they can be trained using ideas such as backpropagation and stochastic gradient descent. When should you use rectified linear units instead of sigmoids or tanh neurons? Some recent work on image recognition has found considerable benefit in using rectified linear units through much of the network. However, as with tanh neurons, we do not have a really deep understanding of when exactly rectified linear units are preferable, nor why. To give you the flavor of some of these issues, recall that sigmoid neurons stop learning when they saturate, i.e. when their output is near either 0 or 1. As we've seen repeatedly in this chapter, the problem is that sigmoid prime terms reduce the gradient, and that slows down learning. Tanh neurons suffer from a similar problem when they saturate. By contrast, increasing the weighted input to a rectified linear unit will never cause it to saturate, and so there is no corresponding learning slowdown. On the other hand, when the weighted input to a rectified linear unit is negative, the gradient vanishes, and so the neuron stops learning entirely. These are just two of the many issues that make it non-trivial to understand when and why rectified linear units perform better than sigmoid or tanh neurons. Footnote. See, for example, what is the best multi-stage architecture for object recognition? Blah, blah, bunch of papers. Note that these papers fill in important details about how to set up the output layer, cost function, and regularization in networks using ReLUs. I've glossed over all these details in this brief account. The paper also discusses in more detail the benefits and drawbacks of using ReLUs. Another informative paper is ReLUs by whatever, which demonstrates the benefits of using ReLUs in somewhat different approach to neural networks. So, I guess something that is confusing me, like, okay, I understand that they can never saturate and why that's good. It means they never stop learning while they still have some weight or output, some activation. But what about once they hit zero? Does that mean they're dead forever and you can't recover them? Or is our momentum and our well, momentum won't save them. Momentum won't bring them back to life because it'll only push them farther negative. No, that's not true. That's not necessarily true. Because momentum changes the weights, so maybe changing the weights could bring them back to life. Regularization is the other thing that changes weights even when the activation is zero. Okay, so maybe those two things can bring stuff back to life. I've painted a picture of uncertainty here, stressing that we do not yet have a solid theory of how activation functions should be chosen. Indeed, the problem is harder than I have described, for there are infinitely many possible activation functions. Which is the best for any given problem? Which will result in a network which learns fastest? Which will give the highest test accuracies? I'm surprised how little really deep and systematic investigation has been done on these questions. Ideally, we'd have a theory which tells us in detail how to choose and perhaps modify on the fly our activation functions. On the other hand, we shouldn't let the lack of any full theory stop us. We have powerful tools already at hand and can make a lot of progress with those tools. Through the remainder of this book, I'll continue to use sigmoid neurons as our go-to neurons since they're powerful and provide concrete illustrations of the core ideas of neural nets, but keep in the back of your mind that these same ideas can be applied to other types of neuron and that there are sometimes advantages in doing so. Alright, while we're reading this, okay, hopefully we're back. Brief network blip, it seems like. Question, how do you approach initializing and researching machine learning techniques that are supported almost entirely empirically as opposed to mathematically? Also, in what situations have you noticed some of these techniques fail? Answer, you have to realize that our theoretical tools are very weak. Sometimes we have good mathematical intuitions for why a particular technique should work. Sometimes our intuitions end up being wrong. The question becomes, how well does my method work on this particular problem, and how large is the set of problems on which it works well? Question and answer with neural networks researcher Jan LeCun. Once attending a conference on the foundations of quantum mechanics, I noticed what seemed to me a most curious verbal habit. When talks finished, questions from the audience often began with, "I'm very sympathetic to your point of view, but..." Quantum foundations was not usually my usual field, and I noticed this style of questioning because at other scientific conferences, I'd rarely or never heard a questioner express their sympathy for the point of view of the speaker. Oh look, we're above 98%. At the time, I thought the prevalence of the question suggested that little genuine progress was being made in quantum foundations, and people were merely spinning their wheels. Later, I realized that assessment was too harsh. The speakers were wrestling with some of the hardest problems human minds have ever confronted. Of course, progress was slow, but there was still value in hearing updates on how people were thinking, even if they didn't always have unarguable new progress to report. You may have noticed a verbal tick similar to "I'm very sympathetic" in the current book. To explain what we're seeing, I've often fallen back on saying heuristically, or roughly speaking, following up with a story to explain some phenomenon or other. These stories are plausible, but the empirical evidence I've presented has often been pretty thin. If you look through the research literature, you'll see that similar style appear in many more network troubles, and hyperparameters and extremely complex interactions between them. In such extraordinarily complex systems, it's exceedingly difficult to establish reliable general statements. Understanding neural networks in their full generality is a problem, like quantum foundations, that tests the limits of the human mind. Instead, we often make do with evidence for or against a few specific instances of general statements. As a result, those statements sometimes later need to be modified or abandoned when new evidence comes to light. One way of viewing this situation is that any heuristic story about neural networks which carries with it an implicit challenge. For example, consider the statement I quoted earlier explaining why dropout works. Footnote. This technique reduces complex co-adaptations of neurons, since a neuron cannot rely on the presence of particular other neurons. It is therefore forced to learn more robust features that are useful in conjunction with many different random subsets of other neurons. This is a rich, provocative statement, and one could build a fruitful research program entirely around unpacking the statement, figuring out what in it is true, what is false, and needs variation or refinement. Indeed, there is now a small industry of researchers who are investigating dropout and many variations, trying to understand how it works and what its limits are. And so it goes with many of the heuristics we've discussed. Each heuristic is not just a potential explanation, it's also a challenge to investigate and understand in more detail. Of course, there is not much time for any single... our learning has basically stopped at this point. So I guess we should stop it here and say the answer was 98.18, which is pretty cool. It's only 1% more than we get by just running it with 30 neurons and 30 epochs, but still. Of course, there's not time for any single person to investigate all these heuristic explanations in depth. It's going to take some decades or longer for the community of neural networks researchers to develop a really powerful evidence-based theory of how neural networks learn. Does this mean you should reject heuristic explanations as unrigorous and not sufficiently evidence-based? No. In fact, we need such heuristics to inspire and guide our thinking. It's like the great age of exploration. The early explorers sometimes explored and made new discoveries on the basis of beliefs that were wrong in important ways. Later, those mistakes were corrected as we filled in our knowledge of geography. When you understand something poorly as the explorers understood geography, and as we understand neural nets today, it's more important to explore boldly than it is to be rigorously correct in every step of your thinking. And so you should view these stories as a useful guide to how to think about neural nets while retaining a healthy awareness of the limitations of such stories, and carefully keeping track of just how strong the evidence is for any given line of reasoning. Put another way, we need good stories to help motivate and inspire us, and rigorous in-depth investigations in order to uncover real facts of the matter. Okay. Okay. So the next chapter is a visual proof that nets can compute any function, which I'm not super interested in, honestly. I kind of already believed this based on the simpler proof from the beginning. So I think I'm actually just gonna read this off stream, and next time we're gonna come back with, well, I don't know, actually. We may already be done learning things from this book. Or like, I don't know if there's anything more for us to implement. Possibly deep learning. We're going to talk about convolution here, it looks like. Which is not actually important for me because my goal is to build an LLM. So, so I may actually read the rest of this book off stream and then come back with what lessons I learned, if any, that will help us build an LLM. And then, yeah, so next time we're either gonna go over some lessons or we're gonna find something new to start working towards. But that's gonna be it for now. I hope this was helpful. Thanks for watching.